A physical crash test is a very important thing. There is a violence in the event. There is a sound that occurs that will alter the way you think about what it is you're modeling.
Running a crash test really helps validate these models and make sure that all the inputs you put into these models are appropriate and correct.
The world's love affair with the car was immediate. But by the 1960s, faster speeds crammed roadways. The fatality rate of drivers had escalated. Then Ralph Nader, a car safety advocate, delivered a crushing exposé, placing the blame squarely on the then three biggest automakers, General Motors, Ford, and Chrysler, and the government's failure to regulate. By 1966, the auto industry was on the run. Nader had won a lawsuit against GM, and a series of congressional hearings led the U.S. government to create the U.S. Department of Transportation. Its mandate? Save lives, prevent injuries, reduce vehicle-related crashes. The question was how to make a safer car. The answer came in the form of a crash simulation program from Lawrence Livermore National Laboratory and a young programmer specializing in bombs. In 1976, John Hallquist wrote Dyna 3D, a program to measure the impact loads and structural response of bombs dropped at low altitudes. Realizing his 5,000-line computer code had massive potential, he released it as open source code in 1978. Through the joint efforts of Hallquist and the car industry, the car companies developed their own crash test software. This tool was game-changing. It enabled them to meet the new requirements from the National Highway Administration and produce safer cars.
If you looked at the decades, say 60s, 70s, 80s, and 90s, the small car of the 90s were safer than the large cars of the 60s. So the cars are safer.
So how did car crash software evolve, and how did it work? Turns out it's elementary.
And the crash analyst would be asked a question. Here is a member that is being proposed for some changes in terms of thickness, the dimensions, and material, for example. Will this pass the crash test? And that's where the crash analyst would take this information and start to build a finite element model.
This is a section of the front rail of Ford GT. The material in here and the geometry of this part are complex, but if you break it down into small enough pieces, those little pieces are simpler. And that's what the finite element analysis does. It's the element that you're talking about, and you can set up simple equations that describe how one little square connects to the next. And because you have the ability to do massive amounts of calculations, you can predict what's going to happen to each one of those elements, and then by aggregating them together, you can predict what happens to the entire structure.
With the evolution of the supercomputers, the number of elements have increased from maybe 10,000 to 10 million.
A physical crash test is a very important thing. The analysts have to be able to have experienced what that looks like. There is a violence in the event. There is a sound that occurs that will alter the way you think about what it is you're modeling.
You can't be 100% sure that your model will perform as physically accurate as possible. So running a crash test really helps validate these models and make sure that all the inputs you put into these models, which are done by humans, are appropriate and correct.
Nowadays, people pay attention to crash test results. The results are published in consumer magazines. They're published in press, and I think that it does influence purchasing decisions are. There was a time when it didn't.
Well, I think we still have a long ways to go in the development of the software to make it even more accurate, make the results more physical, and get to the point where less skilled people can use the software.
The first crash is when the car gets hit. The second crash is when the occupant starts hitting things. The third crash is the internal organs now start hitting whatever part of the human body has been stopped. With the new software, you can model the whole human body. And when you have a human model, you can the understanding of how the injury actually occurs at a much higher level. As a result, what would happen is you take these model results, and you see a certain injury mechanism going on, and then you can go to the government and say that, look, something is missing here in your testing.
At one point now, when we developed the Edge, there were absolutely no fatalities in the Edge up to that certain time. It really has to do with saving lives and mitigating serious injuries. I can't have a better moment of satisfaction more than this.
You see a lot of very bad accidents today where the people walk away, which wouldn't have been possible 10 or 15 or 20 years ago. The software keeps improving, and the designers didn't have the advantage of today's software.